Hello ladies and gentlemen, I'm Barbod Naderi and I'm going to be reporting problem number 12. The problem states that a Wilberforce pendulum consists of a mass hanging from a vertically oriented helical spring. The mass can both move up and down of the spring and rotate about its vertical axis. The problem asks us to investigate the behavior of such pendulum and how it depends on the relevant parameters. Let's take a look at our approach. We are first going to offer an initial observation, which is the observation of the phenomenon, and then we're going to move on to our theoretical framework, which includes qualitative and quantitative analysis. Next up is our experimentation, in which we will describe our experimental setup and we'll compare the results of it with our theory. And finally, our conclusion, which is an overview of the presentation. So let's first start with the initial observation. So as you can see, given an initial push in the vertical direction, the motion, the translational motion in the up and down turns slowly into rotational. In other words, the mass starts spinning around its vertical axis. Now let us analyze this theoretically. So our theoretical framework can be divided into three separate parts. First, we're going to discuss a simple mass on a spring, then coupled systems, and finally, the Wilberforce pendulum. So let's start with the simple mass on a spring. So as you can see, a simple mass on a spring we can find the relevant parameters for it. For example, that includes the period of oscillation, the angular frequency, and the force that it exerts onto the spring. Now, importantly, the position of the mass as a function of time is some amplitude A times the cosine of omega t plus phi, where omega is the angular frequency and phi is the phase angle. And now we're going to discuss coupled systems. So let us define first an equilibrium for the coupled system. So we have masses m1 and m2, and we have three different springs with different spring constants. And now if we push them to the right, if we push each of the masses to the right, we can see that m1 and m2 will have traversed the distance of x1 and x2 respectively. We can find out the force that they exert by Hooke's law, and we can find the positions of them. So notice that x1 and x2 are similar in magnitude and in direction. And because the system is coupled and it is in resonance, the frequencies of both of them will be the square roots of k of RAM. Conversely, if we move them towards each other, in other words, if you do it towards the middle, we can see that solving for the equation of motion, we can see that this time x1 and x2 are similar in size but opposite in direction. So now let's discuss the Wilberforce pendulum. So first, what is it? Well, as it was observed in the phenomenon demonstration, if we give it an initial push in the vertical direction, we can see that over time, the translational kinetic energy turns into rotational. This is a phenomenon known as the transfer of energy. So why does this even occur? In other words, why does transitional motion turn into rotational? Well, if we suppose we have a spring and we denote the end of the spring before compression by an orange circle. So if we compress the spring, we can see that the end has moved down a bit, and that means that the spring has rotated. So if we stretch the spring to the point where a wire is left, that wire will of course be of constant length, and therefore compressing the spring leads to an increase in the number of turns, which in turn leads to the rotation of the spring. Let us now write the equations of motion. Well, the Lagrangian for the system is the kinetic energy minus the potential energy. So we will now simplify the above equation using the Euler-Lagrange equations. And as it can be observed, we will obtain the two equations of motion. So in other words, we will obtain two coupled differential equations which describe the motion of the system. Now, the frequencies, we can substitute in the values of the angular frequencies for the theta and the z directions. And if they are equal, in other words, if the square root of delta over I is equal to the square root of k over m, then that means that the system is in resonance. So now let's see if we can simplify the equations of motion. Well, notice that if the coupling term does not exist, then it will be just a simple oscillation in z and theta. But using the frequencies, the values for the frequencies, we can obtain two, again, differential equations. And now we will assume theta and z as a function of time to be some amplitude a times e to the power of I omega t, where I is the imaginary unit. We will now substitute that into our equation, and we will obtain a quartic equation, which can be reduced to a quadratic equation if we suppose that the variable is omega squared. We can now solve for the two normal modes of the system by the quadratic formula, and therefore we will obtain the values of the system. So if we suppose that this the omega z is equal to the omega theta is equal to omega, then using the binomial expansion for the beat frequency being much less than omega, we will obtain the two following normal modes. Now, in this case, the beat frequency is equal to the difference between the two normal modes. Now, let's discuss periods of oscillation. Well, if the system is in resonance, that means that the period of oscillations in the z and theta direction have to approximately be the same too. Let's now take a look at the effect of gravity. Without gravity, if we were to just push a spring, we can write out the equations of motion, but with gravity, we can see that if a force of mg, in other words, if a weight force is exerted onto the mass, then the equations of motion will just shift by mg. So the gravity has no effect on the frequency. So now we're going to move on to our experimentation. Our experimental setup was as follows. We had two cameras which measured z and theta from the side view and the bottom view. The bottom view will look something like this. We can easily measure the angle by dividing the arc by the radius. The side view is very straightforward to measure. We then transformed these from the data we have gathered using a Python code, and we substituted in the initial values which we found empirically. And finally, now we will simplify the resonance. So we discussed that resonance occurred when the square root of k over m was equal to the square root of delta over I. Now we can simplify this to a much easier equation to deal with, which states that the spring constant k has to approximately be equal to the torsion constant of the spring, delta, over r squared. Now, k and delta have to vary. They are very difficult to vary. But r squared is very simple to vary. So we decided on varying that in our experiments. So now let's move on to theory versus experiment. So we will see that the change in z versus time and the change in theta versus time. So this is a good demonstration of the transfer of energy and the law of conservation of energy. Now we will change R while the mass stays in resonance, and as we can expect, as we decrease R, then the spring constant must increase because R squared here in the equation we derived was in the denominator. So now we will change M while the mass stays in resonance. And we can see that as we increase M, the period of oscillation, the vertical period of oscillation, will decrease. And now if we change M again and compare it to the rotational frequency, we can see that it has, as we increase M, it is proportional to T theta. So if the mass is not in resonance, we can obtain a simple oscillation in theta, but we can get a very unordered change in z versus time. Now, this is the case when the mass is not in resonance. In other words, if the frequencies are not the same and not equal. While the mass is in resonance, however, we can see that as z goes by, then the maximum values of z occur at the minimum values of theta. And this is exactly the transfer of energy we're looking for in our experiments and in our theory. So now we will conclude the presentation. Well, first we looked in our theory at simple harmonic oscillators. We discussed each of their parameters and we moved on with that knowledge to coupled systems. Then we moved on to the Wilberforce pendulum, which was our main objective. And we first qualitatively described why does translational motion turn into rotational. Then we used the energy or the Lagrangian approach, and when we simplified them to obtain the two equations of motion for the pendulum, we then simplified them even further to obtain the normal modes of the system, and we discussed resonance. Now we will see the phenomenon only if the frequencies are approximately the same. Now let the difference between these frequencies be delta omega. So the closer that delta omega is to 0, the less energy is lost and the better we will observe this phenomenon. So we found the normal modes as it was discussed in our theory. And then we simplified our equation which we derived for resonance. Now let's conclude our experimentation. So we showed our experimental setup, and then we plotted them using a Python code, and we were able to get the experimental plots. Now we had a few plots which were supposing that the mass was in resonance, and then we plotted when the mass was not in resonance versus when the mass was in resonance. And you can see the clear difference between the two modes here. These are our sources from which we have gathered our data and our theory. And that is the end of our presentation. Thank you for your attention.